Thanks for the invitation to come here today. It's always nice to have a look around and see what's going on, and the ASRC seems like a really exciting institute and good opportunities there. So today I'm going to be telling you a little bit about my research and in particular how we're looking to do research now in terms of from the traditional mode of collaboration where you would approach somebody and ask them to look at one aspect of the system that you're working with to now having a fully integrated approach. So the research that we look at is mainly in the application of computational and theoretical methods to solve chemical problems or problems of interest to people. And so as a result of that, we do a lot of collaboration with experimentalists. And as I was saying, so this is a picture of my group from early this year, I think, late last year during the autumn. And of these people that you see here, nearly 2/3 of the group is actually split doing part of their PhD with experimental and computational. So we only now have 5 people who are purely computational in our research. Most people literally come in and out of the lab and into the computing office every single day. And this has benefits in that we have greater integration of techniques within the project. So the students are not only able to calculate an infrared spectrum, but go and make an infrared spectrum. They go and actually measure the UV vis and then find out what they do when they calculate the UV vis. And they understand how these two things work together and what are the different model parameters. So they end up with a greater breadth of knowledge in what they're doing. They also get some greater exposure to different supervising styles, which is sometimes worthwhile if somebody's harder than another person's. They have an ability to be flexible within that. And often we find now that the students actually really enjoy this. So the people who only have purely computational research projects are now coming to me and saying, I'd like to do some experiments as well, because they see the benefits of this style. So that's sort of the approach that we're taking in terms of how training of students. But the areas that we're working in I've sort of listed here as molecular reactivity, molecular properties, and nanoscale structures. These are the sort of main research areas, and I'll give you a quick overview of what I mean by those. But that's sort of the applications that we're doing. We do some method development within these areas, like purely computational and theoretical method development, but it's always within the framework of trying to solve a problem. So we don't sort of do method development as a default, but if we need a method, for example, that couples one of the things we're working on at the moment, an atomistic and a coarse-grain method, then we do the development to make sure that we have a program that is able to do that coupling. But if we don't have a problem to solve, then we don't do it just for the fun of it. I guess that's what I'm saying here. So within molecular reactivity, the basic approaches that we are looking at is either we want to rationalize reactivity. So we have something that works. We know that we have a reaction that occurs, and we want to understand why it occurs and how it occurs. So that's what I mean there by rationalizing reactivity, because once we understand how or why a reaction occurs, then we can work out what are the principal forces that govern whether or not that goes ahead. And then if we do that, then we get to the more exciting part, which is then designing favorable properties. And I'll give an example of that in part of the talk today, how we've taken a system which once we've studied it to work for a certain type of substrate, we were then able to go on and modify the catalyst so then it works specifically for a different type of substrate. So we've applied this to polyoxides, organometallic catalysts, mixed metal catalysts, and organic superelectron donors. That whole type of process of starting from basically understanding what the experimentalists are seeing to being able to predict properties for their future and help them develop the chemistry that they're doing. So in the molecular properties, we take the same type of approach, but things are slightly different. With molecular properties, we always need to benchmark our methods. So this usually forms the first part of any type of project here. Because with methods like density functional theory, sometimes they'll work for a certain property and sometimes they won't. Often you need to work out with the type of application that you're doing, whether or not your methods will even work. Once you've done that, you can then start correlating the properties that you're calculating to some type of structure, and then you start to get insight, and that's one of the main things that we're doing there. And if you have that, and if one of the properties you actually want, then you can start to modify the structure to get the type of property that you're looking for. And there we've done things like NMR, measuring, calculating spin-spin coupling constants and chemical shifts. We can calculate Mersbauer spectra to investigate spin states of molecules. Infrared spectroscopy, which can be used as a tool in structure determination. Same as UV vis spectroscopy, which can tell you things about stacking or also the electronic properties. Nanoscale structure with the movies, because there we're doing atomistic molecular dynamics and coarse-grain molecular dynamics, so we get things moving around a lot more. And there we're again taking a similar sort of approach. The first step is always to understand how these things occur. So what are the governing interactions in self-assembly? And then we might even use density functional theory to look at the specific interactions. So the example up on the right, I can't move around and point too much, but the example in the far right that you're looking at is looking at hydrogen bonding interactions and how these might dominate the anti-parallel beta sheet stacking. And then we can, once we understand those interactions, we can look at the mechanisms by which things can self-assemble. What are the things that could dictate whether or not self-assembly occurs, and if it starts to occur, then how they stack together. And then once we get these self-assembled structures, what are the properties of them? Can we look at catalytic self-assembled structures, or do we have things which make stiff gels or not stiff gels, and so on. So in particular there we're looking at things such as surface binding interactions, so binding things like peptides onto gold, and why a certain sequence will bind better than another sequence. I've put computational drug design in there because we do computational drug design. It doesn't technically fit as easily into nanoscale structures, but you can say that a protein is a nanoscale structure, and so we dock into these as well. That's just a sort of one thing that we do as well. Molecular capture is also of interest, so that's looking at using peptide sequences to recover, in this case, a type of fertilizer that was in the system, and how to use peptides as a way to capture those molecules out of the aqueous environment. And finally, biomolecular self-assembly. In there, we're working predominantly with the peptides and functionalized peptides of sort of di- and tripeptide length. Okay, so that's sort of a quick overview of the three different areas. Now, what I want to do now is give you a sort of more specific example of each one of those. So the first case that I want to look at is molecular reactivity. And I'm going to be talking about highly active iridium-1 catalysts. So this is for catalytic hydrogen isotope exchange. So this is work done with our experimental colleagues, Billy Kerr at the University of Strathclyde, and we have a joint PhD student who works both in the lab on these things and also computationally with me, and that's Mark Reed. Funding from him from the Carnegie Trust. So a little bit of background. Hydrogen isotope exchange is an important reaction in the pharmaceutical industry because they want to be able to selectively label potential drug molecules to see where they go in the system, but also if they interact, if they can regioselectively label these things, then they can look at the type of interactions that are occurring through NMR to understand what the binding site is and so on. So they want to be able to regioselectively label these things, and they also want to be able to apply this to fully functionalized molecules. So it's relatively easy to label something which is just all carbons, but once you start to have heteroatoms in there, then these heteroatoms will bind to the catalyst in certain ways, which makes it quite difficult to label them. And the thing is, they want to do all this in a one-step process. So we've been working with the Kerr group for a few years now, and have a pretty good understanding of how these works with iridium catalysts. And we have a couple of examples here of the type of iridium catalyst. So the first one, which you see next to regioselective labeling, is the standard one that we have been using for things like acetophenone, which is the NHC and triphenylphosphine. You see the cyclooctadiene will actually dissociate once you put it into solvent, and then you bind H2 to it, and you end up with an octahedral complex there. And then from that you can do the you could do the deuteration or tritiation. The alternative that you see at the bottom is where you replace the triphenylphosphine with chlorine, and this one we've found to be quite an active catalyst in the case of sulfonamides. And again, we sort of understood that the process of removing the triphenylphosphine and replacing that by chloride, actually, we understood that the reason that this made the catalyst much better for sulfonamides was that we were removing a lot of that steric bulk, and we were actually getting coordination through the NH2 of the sulfonamide. So when the triphenylphosphine was there, we had very bad labeling, but once we changed that to a chlorine, we were able to label at up to 98% deuteration levels. So we were able to understand then that what the controlling factors were. So then when we moved on to the next thing, we thought, let's have a look at sulfones. Sulfones are also an important class of drugs in the pharma industry. We used the same catalyst which we had for the sulfonamides, which was the chlorine ligand attached to the iridium, where we were getting up to 90% deuteration. Well, in this example showing here, we had 90% deuteration. But once we changed over to the sulfone, our deuteration dropped off down to 70%, which is much lower than we would hope to see for these type of things, especially at the conditions required. Just to make sure that something strange wasn't happening, we tested the sulfone with our traditional catalyst, which had been shown to work well for a variety of substrates as well. So this is with the triphenylphosphine and the IMES NHC, and we see that again the rates of deuteration is extremely low at 9% D. Just for comparison, you see if you use the acetophenone, actually with that traditional, well, the base catalyst that we considered, it's actually 90% deuteration level. So the system overall worked, it was just not working for our case of our sulfones. And the problem that we think was happening there was that the sulfones are, firstly, they're tetrahedral and they're sterically large, but in addition, sulfonic oxygen atoms are poorly coordinating. When we had the sulfonamides, we were actually coordinating through the nitrogen and had an additional HCl interaction that was helping to stabilize those systems. Once we switch to the sulfones, we lose that. And so if we have, in this case I'm showing on the top the acetophenone, you can see that that's really quite planar, and that's able to sit into that equatorial plane. So the big blobs are the NHC and the triphenylphosphine in that case. With the sulfone, because you're now in a tetrahedral environment, you're getting that interaction, which is unfavorable as well. So we thought, well, if that's the problem, then one way to do that, of course, is to remove that and force these ligands into a more favorable environment. And you can do that through clipping the two large ligands together. So the monodentate ligands, where you have the NHC and the triphenylphosphine in a separate, coming in separately, these are always formed trans to each other and they take up quite a lot of space. But if we create bidentate ligands, then we're able to clip these together so that they coordinate to the iridium metal center in a cis fashion. So they're going to be sterically smaller. You're going to create a much larger place where you can fit that sulfone in. So we knew what we wanted. We wanted some type of bidentate chelating ligand. And one can think of a variety of different types of ligands which you could make that might be able to do this, but the question is which one is going to be the best one, which one to try that will make your life easier. To go ahead and make all these in the lab is going to A, be expensive, but B, it's also going to be very time consuming. I mean, that represents months and months of work just to understand, just to find one decent substrate. And so we wanted to use computational methods to essentially cut this list of some 20-odd different ligands down to 2 or 3 that would make sense to use. So in these types of calculations, we are usually using density functional theory. This was employed for all these calculations. All structures were optimized using the MO6L functional. These are just technical details I put up in case somebody has an interest in this and wants to ask a specific question. We use Gaussian for all calculations, but I'm happy to talk about that if desired. I should say that one of the reasons we were able to do this is because we already knew a lot about our system. We had done the calculations on the basic system, so we knew that the binding was going to be the critical event, whether or not we were able to bind this thing in the first place. So what we decided to do was calculate the binding energies using counterpoise corrections, but we calculate the binding energies because we know that the activation barrier actually doesn't change that much. The activation barrier is the oxidative addition. We're aware of this, but the question is whether or not we have good deuteration in this case is simply due to whether or not we're able to bind and how strongly we're able to bind. So we calculate the binding energy using counterpoise corrections in the standard way of Boyes and Bernardi, and we get a whole heap of binding energies like this. Now if you see the red bar, this is with the IMES and triphenylphosphine and the trans arrangements of the standard catalyst. You see that our binding energy is actually about 15.5 kcal/mol, which is, I'll show you in the next slide, it's quite low for the sort of binding event. So essentially this binding of the substrate has to displace two solvent molecules. So it has to be a stronger enough binding event that it can release the two solvent molecules that will then allow this reaction to occur. But you can see with our clip species that when the blue case we have the tether of the 2-methyl tether to the phosphine, and on the green case we have the methyl phenyl tether to the phosphine. And all of those cases where we have the bidentate, we're getting much stronger binding, down to 33 kcal/mol. The exception is the final purple one, but that has phosphine with bis adamantyl ligands, which are just quite a lot different, bulky bridge ligands. So we can sort of ignore that one. And if we look in comparison to the acetophenone, so now we have this red bar here, then you see that we're getting, so acetophenone for this IMS PPH3 works extremely well, and we have a binding energy of about 23 kcal/mol. So we know that we need to shoot in that sort of binding energy area of about 23 kcal/mol. If we use the IMES CL or IMES PPH3 with our sulfone, we're up around 15 kcal/mol, so that wasn't working very well. There was an additional complication, and that was how the sulfone actually approaches the catalyst. You have two options in this case. You can either bind with the CH coming into the equatorial plane and the oxygen binding into the axial plane, or the inverse of that, where you have the CH in the axial plane and the oxygen in the equatorial plane. So we needed to consider both of these because we found that the energy difference was quite small. But one needs to check both of these in order to make sure that that's possible, so you can imagine the additional calculations required to build all these different geometries. It's quite a lot of work, but Mark managed to get all this done and create sort of then using the Boltzmann distribution, working out what the population of these various things would be to create a new averaged energy of binding, and was able to still find these strongly binding cases for the dimethyl clip species. And so from this large list of 20-something ligands, we were able to cut it down to about 3. One which is similar in energy to the monodentate ligands for acetophenone. This was the second most efficient one in blue. And also then the most strongest binding one and the least efficient binding one for the blue series, just to test that it wasn't then, that it still was as we expected to be a binding energy case, and that we weren't altering the electronics significantly by changing to a cis structure. I can't at this point, because we're doing this work with AZ, tell you which one worked the best, but I can tell you that we did indeed get one which worked extremely well, and we were able to get 98% deuteration for our sulfones in a similar way to our sulfonamides. So from reaction mechanism studies, we were able to identify the steps that govern activity and selectivity. But once you have that reaction mechanism, if you're going to want to screen different possibilities, it actually becomes very complicated to do this for all catalysts. So instead we use structural and electronic descriptors which allow us to identify what is the important thing that we're going to need to change the primary thing. Now, it doesn't tell us everything, but it tells us what we should focus on if we want to develop new catalysts. It's difficult to average over various isomers, but it's possible to do that as long as you don't change your molecular mechanism by moving into a different state, because then the whole basis that you're saying that you can use this outline fails. And then once you have that done, you can use screening approaches to rapidly assess the viability of potential catalysts based on these predetermined criteria. The thing is, of course, you only get what you look for. If you're screening for ligands that are clipped, then that's what you'll find. Yeah? I mean, you can't, if the mechanism changes for a different catalyst, which actually would have been so much better, you don't see this because you only sort of screen for what you think will be the best case. So, molecular properties. I should say at this point also that I'm happy to take questions during or at the end. Themes will change as we go through. So if anybody has burning questions on iridium catalysts, they can ask it. I'm also happy to. Yeah, Harash.
So you mentioned about the the evaluating how the molecule bind to the structure, and you mentioned that activation energy is not that matter. It's more how the binding energy is high or low.
Mm-hmm.
Could you say a little bit more? Why is that? Why binding energy is just matter for the activity?
As a catalyst, it works very well. The actual exchange has nothing to do with that sulfone part. It's actually still just pulling off that hydrogen which is attached to the phenyl ring, which essentially stays the same. So the energies for that's going to be around 18 kcal. We know that that works. The deuterium is over here. You will oxidatively add to the metal. Then you'll have a switch in the deuterium hydrogen, and the deuterium pops back on, and you reductively eliminate it. So what happens over here doesn't concern so much that activation energy step. The question is, how do you get to that point where that's aligned properly? And that's the binding energy. So if you change that sulfone, then you change that alignment.
Well, stronger is better, definitely. Or I was wondering, maybe sort of intermediate binding strength, not too strong but not so weak, might work better in terms of that.
Yeah, we also believe that as is an important thing, and that's why we tested also ones in the middle. So ones which give similar to what we saw for acetophenone, which we know works very well with a binding energy of 23. So we were conscious of this possibility. That, I mean, with reductive elimination, if it's so strongly bound it doesn't want to eliminate, then that's going to stop your reaction. So yeah, you do want to have a balance there.
When you have been looking at the binding energies with M06L, have you found is there experimental binding energy available? So like you could comment on how good M06L is to like describe this kind of systems, because they are metal system and not peptides, but 06L were bad for peptides. So I am not sure how well it performs with this kind of systems. So I was just wondering if you had any comment on comparison with experiment or other methods.
We don't have any experimental binding energies to work on with these systems. We know we do have kinetic data for the actual reaction mechanism. That's not the binding energy. I appreciate that, yeah. But the interaction with the metal will somehow be reflected in how well we can calculate the kinetics through the kinetic isotope effect. And MO6L works well for that. We get very good agreement. We're also tested this previously for looking at the binding to solvent. So one of the things is, how well does this work in different solvents? If you're displacing the solvent molecules, then you want to be able to determine that binding energy with the solvent molecules so that you're competing with. And so we've tested this in different solvents experimentally, and we're able to reproduce the correct order with our MO6L through the binding energies. So for specifically, do we have a binding energy for this? No. But we have some data around it which suggests that it works reasonably well.
So basically, you could have tested this method on other experimental data, and it worked for that thing, so it should work for the binding energies too, right? Right.
Yeah.
Okay. Thanks.
Okay. Let me tell you the properties. So this will be a little bit more speculative, this part of the talk, because it's something that we're doing. We have done a little bit before, but the question is how to move this forward so that we can look at how to develop organic photovoltaic devices. The main challenges that we see that we can sort of start to contribute to in terms of OPV design is the first one, which has been a lot of work done already, which is in HOMO-LUMO Gap Prediction. Morphology of the devices, whether or not we can get some type of control over that, will be an interesting area. And then the third part, which really seems to be underexplored, is the idea of the acceptor compound. So a lot of effort's being put into developing new donors for these types of systems, but the acceptors is pretty much restricted to fullerene at the moment. Because it works well, I should say, not because of any other reason. Okay, so the first one is, why is HOMO-LUMO level control important? And the reason is that if you can determine the HOMO-LUMO energy levels, then you're able to predict properties you're able to influence properties rather, such as electron hole injection, charge transfer, the open circuit voltage, and absorption. And it's not just the energy gap which is important, but you actually want to match the energy of your donor's LUMO closely to the acceptor LUMO, so you can get this charge transfer occurring reasonably well. So the challenge is not just the gap, but it's the absolute energy level, and that's what makes it quite difficult rather for DFT methods. So extensive research has been done and has been carried out in order to determine optimum HOMO-LUMO levels, and what they found is that once you start to get these, then you can relate these levels to the open circuit voltage, which is essentially then going to be directly related to your power. So assuming good charge transport, fine control of the OC is able to give you maximum performance. And there's this graph from this paper by Brabick and company, which is about moving towards 10%. So when we're talking about OPVs, we're still really talking about trying to get 10% efficiency, which would be very good. I mean, if you look at your metal type, or your metal photovoltaics rather, then you're up around 15% and potentially higher in some cases. But with OPVs, the ones that are out sort of at the moment are more like 6% to 8%. So we're still not close to that 10% mark. But Brabick and company produced this graph which shows you, is that moving? No. Which shows you on the y-axis the LUMO level of the donor, and if you then can match this to the HOMO level, then you're able to get this band gap, which will show you the power conversions efficiency, so you want to be down in this lower right-hand corner. So the current prediction methods for HOMO-LUMO level are typically done, and the way we've done one as well, is using small sort of correlation graphs where you use a similar type compound and then make variations on that compound, so vary the substituents. And this you can get decent correlations with. That sort of works quite well. And so you can make a family of compounds and then predict which sort of modifications to that you should make to get better performance. The only problem is that to move this beyond that similar sort of motif with variations, it doesn't work. The correlation no longer carries over, and that's because you're predicting sort of relative HOMO-LUMO gaps. I just mentioned this, we're not the only people looking at these things. There's the very big Harvard Clean Energy Project, and this is a massive project where they're using sort of distributed computing throughout the world. Tens of thousands, millions of computers sign up, and they sort of calculate randomly these HOMO-LUMO gaps using distributed computing. And so here they're trying to look at making some correlation with across different motifs, but you know, I'm not saying anything bad about them. They're doing a really good job, but you see the error bars on these things. I mean, they're bigger than the correlation themselves, so it's still very, very tricky, even with all that massively distributed power. There are many reasons why that is. If you use density functional theory, which we're using, then you have to optimize all your structures to start with, and these optimizations are costly, especially once you start to move to larger and larger molecules. These things are hundreds of atoms, and so then optimizing them takes quite a lot of time. Then you have the issue of the reliability of the optimized structures. So because they're quite large and they can move around, you get stuck in a local minimum, and that local minimum may not be representative of the system that you have experimentally, and so the gap you're predicting then depends on the structure. You've got the wrong structure, so you're in the wrong place. You also have the question of morphology, solubility. These two things aren't considered when you're doing these HOMO-LUMO gap predictions. And the difference in chemical moieties, as I've said, still requires new correlations, even if you get everything else right. So solutions to these, one of the things that we're finding is that we can do semi-empirical optimizations using things that are quite good semi-empirical methods, so PM7, P2G, and so on, give reasonable structures, because internally these units are quite rigid. You have aromatic groups, but they're connected, and you just need to consider how these how this rotation around the bonds is, which semi-empirical methods do reasonably well, and then use DFT single point on top of that to get some. But you know, remember, you're just trying to get a correlation here, so you don't care about the absolute numbers as long as you get the right structure. And if you use conformational search programs, then you can get around this question of which is going to be whether or not you can get out of this local minimum problem. So in terms of the morphology, I'll show you here. So what you're looking at as sort of functional dependence, we see that actually putting in more Hartree-Fock doesn't make much of a difference. We get reasonable R-squareds for the HOMO-LUMO gap. So the gap we can do pretty well. So 92% correlation coefficients there. But we're still miles off in predicting the absolute HOMO level or LUMO level. We can get the gaps quite reasonable, but if you look at the HOMO, you know, we get a correlation with an R-squared of 0.59 in the case of MO6L. So it's pretty much in the right direction, but a long way off from being exactly what we want yet. But this is a known problem with density functional theory, that predicting orbital energy levels is not really appropriate, even if you can consider it that way. Okay, so we can get decent correlations within a set if we use this procedure for optimizing and sampling for the different conformers. Then the next thing, one of the big problems with developing these OPV devices is morphology, and that is that you want to have some type of structure to your desired layers. So if you could control the way that occurs, then that would be a very beneficial thing. So one of the things is, if you could do that through self-assembly, then you have a lot more control over it. The other thing is that if you could understand how your donor is interacting with the acceptor, then you could start to get these donor-acceptor ratios predictively, rather than the way they're doing at the moment, which is to have to mix these things in various sort of optimization studies in the lab. And then once they say, if they do the spin coding process of applying these, this might be completely messed up, and it becomes very difficult. So if they can get away from having to use these type of approaches, then they're able to instead control the actual way that the donors and acceptors are spread out, and that's what we mean sort of by the morphology. Some examples here of some of the systems we've looked at that seem to be quite good are these cruciform donors with a germanium spirocenter, and these sort of lock together, and we have well-localized HOMO-LUMOs, and so we get good charge transfer across the molecule. That's the sort of, and they self-assemble. They have good stacking units which work really well together. If you take the example which is under the not so good, you have these many rotatable pieces and you have the large hexyl chains, and they really pretty much monodisperse across the system. So we can tell that they interact well with the fullerene, but they don't have good morphological properties. So in all these cases that we've looked at so far, the acceptor has always been this PC61BM, sorry about that, which is essentially just a fullerene molecule with a benzo methoxy group on it. The problem is there are many potential interaction sites with the fullerene. Now, our donors are quite large, but they could interact on any component of the fullerene, and the computational cost then associated with calculating this donor and acceptor together is very large. So the question is whether we can have acceptors which have favorable properties and that are also small enough that they become more controllable in terms of how they interact with the donors and therefore become sort of part of a more fixed aggregate. If we can do that, then we'll potentially be able to say how we can, even if they're not as good as the fullerene, but if we have some control over where these interactions, what's dominating them, then potentially we can scale this up into the larger systems. I've just given here a reference to a paper where they've sort of, in the last year or so, started to talk about developing new acceptor molecules that have interesting properties. This is not stuff that we've done, but it is interesting to see that other people are also thinking about trying to fine-tune these acceptor components. So in terms of the perspectives here, as I say, the issue with optimizations being costly, we've sort of gotten around that with these semi-empirical methods followed by DFT single points. By using conformational search optimizers, we're able to be fairly confident that we're getting a reasonable structure. From the morphology side, we're looking at different alternative donor-acceptor combinations and trying to utilize self-assembly as a driving force to get some control over the morphology. But we're still, it's down as a plus minus. I don't think we've in any way solved this yet, but I think that there's the potential that we can move that forward realistically to get to some solution. The difference in chemical moieties requires new correlations. That's true. I don't know how to get around that. I mean, you need to predict absolute HOMO-LUMO energies. The way to do that is to come up with, to move away from DFT, but then you have the issue of cost to get absolute HOMO-LUMO energies. So that one's on the to be done list at the moment. But it's clear that if you want this, then you need to predict this absolutely. Any questions on this before we switch gears? Rashi?
So for the morphology calculation,
Yeah.
is this in solution, this is in dry state?
At the moment, the things we've done have been in the gas phase. So they've been considered in a dry state. You would want to consider the whole solute. Well, you evaporate these things. But I think if you were going to look at the MTE simulations for them, then you would do them initially in the solvent and then dry them off dry them off experimentally, but then they should be fixed in that structure already. So we would do the actual simulation work in the ground state. What we're looking at the moment is trying to decide whether we can get an acceptor which will. So we're only now at that interaction stage of what's the governing interaction here. So we haven't moved up to the large scale. How can we actually simulate this morphology? Yeah.
So potentially, once you predict the
Yeah.
solution, then you can somehow dry out, you can sort of predict.
Yes, so we would expect that our solution state would be a reasonable indication of how it should look once you dry it out. Moving on. So the third thing I'm going to do today is talk to you a little bit about our nanoscale structures, and within this, I'll be talking about virtual screening for new biomaterials. And so this is, I didn't mention this at the beginning, so this title, Reducing Molecular Search Spaces, I'm hoping a little bit of that's become clear from what I've been talking about so far, but it's about trying to make the job of experimental colleagues and the design process a little bit easier, from cutting down from enormous search spaces. Okay, in the catalyst we had sort of a selection of 25 down to 3. In our devices, it's about how can we not have to test all the different donor-acceptor ratios or all the different types of acceptors. How can we get something which is more meaningful? In this case, we're going to be looking at peptides and how we can try to find materials with specific properties before you need to go into the lab and synthesize them all and characterize them and test them. So this work was done with a graduate student who's now a postdoc, Pim Fredericks, Gary Scott, who's between Ryan and myself's group, myself and Ryan as well, who did all the experimental work. So biomolecular self-assembly, we're interested in this because of the applications that it has to biomaterial science, because if we use short peptides, then these are going to be more biologically acceptable. You don't have as much issues with toxicity and so on. We have seen that these are able to self-assemble in certain cases, the most famous one being diphenylalanine. And there are very common motifs that you also see in sort of the protein science. So you can see things like alpha helices form, beta sheets, coiled coils. From a computational point of view, what we're looking to understand, as I've sort of said, is that process of saying, well, all right, well, what are the governing interactions? If we're able to understand that, can we determine the molecular structure of nanomaterials? If we're able to look at that on a sort of atomistic model size, are we then able to move on and say, all right, we can understand how these things are forming, we can determine what they are, can we now predict them in all cases? So the self-assembly of peptides. For that process, we use a number of different methods. For the fine details, how they're interacting, we typically look at density functional theory to get relevant binding energies. If we're looking at packing arrangements, so how these molecular structures form, then we usually need something like atomistic molecular mechanics. And then the third step, if we want to look at the process of self-assembly and the different phases that occur, then we need to run this on longer timescales, and so we use coarse-grain molecular dynamics. From quantum chemistry, we get accuracy. We have to get input for spectroscopy, and we can give back this sort of spectral data, but we're really limited in our system size to something in the order of 10 monomers for the sort of monomers that we're looking at, di and tripeptides. And we have no dynamic information as well. We really always do these just as static structures. So they're able to give us detailed information, but only for small parts of the system. If we use atomistic molecular dynamics, then we can get detailed structural info about directionality of hydrogen bonds and so on, but we are really biasing the type of structures by our input structures. If we push these things far in the time scale, we still are only in sort of the hundreds of nanoseconds, and when we want to see assembly, then we're looking more at microseconds. So our value for CPU hours is relatively low if we don't introduce some bias. The final one, which I'll be talking about predominantly today, is coarse-grain molecular dynamics. And in this case, we can get long time scales that are accessible, or we can screen things very fast. We're able to get tertiary type of structure information. I'll give a quick example of that, but we certainly lose all our detail. The parameterization of these things is not straightforward, but we lose any detail about directionality of hydrogen bonding because there are no hydrogens, as we shall see. So the coarse-grain approach is to take multiple atoms and put these into one bead. So I've highlighted there sort of, this is the case for diphenylalanine. You see on the backbone, the whole backbone becomes one bead, which is this red bead here. And then the ring is condensed down to a 2 heavy atom to 1 because it's a ring structure, but typically it's either 3 or 4 heavy atoms become one bead. And so in the case of phenylalanine, you go 2 to 1, so you keep that type of ring structure. We're using the Martini force field within the Gromax package. Because you have much heavier atoms now, well, they're not atoms, they're beads. You have much heavier beads, you're allowed to take much larger time steps. So a typical time step in an atomistic case would be 1 to 2 femtoseconds. Here we go 20 to 30. And if we have such a large time step, we're already getting an order of magnitude speed up. Overall, we get about 3 orders of magnitude speed up because we have much larger systems, much fewer atoms compared to all atom simulations. And in our simulations that I'll be talking about today, we did all these in the zwitterionic state. So one of the first things that we did was we wanted to make sure that this method was useful, that it was able to, these are a lot of simplifications that we're making. We're taking away all our hydrogens, we're losing a lot of detail in the system, so we wanted to make sure that it was able to actually tell us something useful. And so we started off by screening all 400 possible dipeptide combinations, so 20 amino acids, 400 possible dipeptides. We put 300 of these in a box. We have water in the box as well, so we explicitly solvate all of these things. We run them for 100 nanoseconds, which in coarse grain corresponds to 400 nanoseconds, and we see what we get. What we found was we ended up with a lot of data. I mean, you run 400 simulations for 400 nanoseconds, you get a lot of information. This takes up a lot of space. So we need some way to talk about what it is that we end up getting. And we decided to look at, as a diagnostic, what we call the aggregation propensity score. So we could do this by considering the solvent-accessible surface area of our individual monomers in the randomly distributed state. So when it's randomly distributed, it's going to have a high solvent-accessible surface area. Once they start to aggregate, you're going to lose some of that area because the faces are going to come together. And so we can take the aggregation propensity as the ratio between that initial and final box. If we're able to plot that, then we can see how that changes over time. And we see for our plot here, what we're looking at is the aggregation propensity for all 400 dipeptides. We use the single letter code on the X and Y axis. And sort of unsurprisingly, what you see is that if you have a hydrophobic peptide like phenylalanine, then you see these squares are much darker red colors, or tryptophan, you get the same type of effects. But there were some interesting ones in terms of the S and H. But at least we see that the coarse-grain approach is able to provide us the type of information that we're looking for. Do these things aggregate, yes or no? We then wanted to find out whether they gave us any information on self-assembly. And for that, we took probably the most well-known example, which is diphenylalanine. And as I said, for coarse-grain, coarse-grain is not particularly great for secondary structure because you don't have any information about hydrogen bonding. But for some type of, let's call it tertiary structure, how these things pack together, you are able to get some information. So I'll just run this movie. So we started from this large box, randomly distributed. So now we have 1,600 molecules. And what you see is that very quickly they aggregate together into the type of sheet-like structures, which then are able to curl over on each other to create these micelles. And then the micelles are able to come together to form these longer unidirectional tube-like structures. And this, there's some information in the literature about diluting the system and this transition from tubes to spheres, so there was some indication that we were getting the right type of structure. This is the sort of snapshot version. So at 0.2 microseconds, we were already getting this aggregation, which is what we were seeing in our 400 nanoseconds, that these things aggregate quite strongly. By half a microsecond, we're into the sphere-type state, and by 1.5 microseconds, we get our tubes. And what you're seeing, I've just visually cut off the end of this to show that it is in fact a tube and not a fiber inside. The blue is the water, and so we indeed have this FF tubes, which is seen experimentally. And the diameter of these that we calculated is in the right order of magnitude, so it's about 70 angstroms to what is seen experimentally. We get rotation around the rotational order of the side chains are at the right angle as well. So we're doing a pretty good job just in terms of the general structure. So basically we said, okay, we sort of trust that our coarse-grain approach is giving us something useful. Can we now apply this to a much more, a system with more potential properties? And so we went then to look at the basic approach of, can we use coarse-grain as a screening method? So what we want to do here is just try everything. Try all our possibilities. So we have 8,000 tripeptides. Let's just screen all of them and then apply a filter on top of that to say, okay, what we want is a peptide that will self-assemble and do something nice. So in the case that we're going to look at, the do something nice was and form a gelating species. Well, can we get something that will not just crash out of the system as soon as it self-assembles, which is what you see with things like FF. So when we're doing 8,000 things, we decided to use a shorter initial screening phase. So we did 50 nanoseconds for initial aggregation propensity to see whether or not these things would come together. For the interesting cases, I'll define those in a moment, we did a full 400 nanoseconds to find out whether or not our aggregation propensity was working at 50. This comes to about 160,000 CPU hours. So it's not for free. But if you get enough CPUs, then you can. If you get 1,000, then you can do it in 160 hours, which is only a few days, and then all of a sudden you have all 8,000. So it's still much, much cheaper than doing them all experimentally. So we had our 8,000 tripeptides. We used an automated analysis approach with the AP score, and we said if AP was greater than 2, it would indicate a good potential for assembly, or at least for aggregation. Then what we said was we want these things to stay in solution if they're aggregating, and so we need some type of solubility as our second filter. And so there we came up with the hydrophobicity corrected scores, our APH scores, where we just used the AP squared times the log P, where the log P is, you can see that there, where the log P we're using is the Wimley-White score. So this is, essentially we're just using an additive approach for each of the amino acids, have a log P, and we just add those together for our tripeptide to get a AP score. And this is normalized in some way. So if we just initially plot the AP score, okay, against the amino acids, what you're seeing here. So we're starting hydrophobic in the bottom left corner and going up to most hydrophilic. And if we're just looking at the AP score, so this is not the hydrophobicity corrected one, this is the basic AP score, you indeed see that it's sort of much darker in this bottom left corner, and as you increase hydrophilicity, it goes up. This is, of course, much more, lots of dots, and they're very hard to look at when you're first seeing them. I've looked at them for a while now, but essentially you're looking at the first amino acid on the x-axis, the second amino acid on the y, and within the block you have all the N-terminal amino acids. So you can sort of go along and pick out a dark square. I'm going to have to walk over here to do this. You can sort of pick out a dark square here and see that this is sort of V, A, W. And it's dark, so it should potentially have some type of aggregating ability. Well, the fact that they're all down here shows that you have your AP score, and indeed predict hydrophobic things will aggregate. Once we correct this using the hydrophobicity score, you see a much different, more well-distributed sort of darkness to this graph, and so you still have, your W's and F's are still going to be quite dark because the AP score is quite strong, but now they're much more hydrophobic, so this is going to count against them when you're using the hydrophobic corrected score. And from this, we were able to pick out a number of different examples. The ones we picked out were the AP score greater than 2, just to make sure that indeed things were behaving properly. And then we picked out the top 400 from our APH score. And so what you're seeing here is two things. Firstly, the green is showing you all the ones which were picked out, which is the sort of top slice, and is the AP squared times log P, so you have a quadratic function. So you can see that shape sort of already there on the green one. The second thing is that, we always say hydrophobic there will aggregate, and that's true when you get to very hydrophobic. I mean, you see to the left-hand side of your graph, then the aggregation propensity is very high. But if you sort of move towards medium hydrophobicity, so from say -2 to 4, you get a really large range in the aggregation propensity. And so there is some type of weak correlation between the two, but it's not exact. I realize I've been going on now for a little bit, so I'll try to pick it up and finish off here. So we have some of the snapshots here at 400 nanoseconds, and you see that we're starting to get some type of structures that are forming some type of aggregates. For the most interesting cases, the ones that we find are really working well, we're able to push these to the microscale time second. In terms of how well we're doing, I'll tell you about our comparisons with experiments from the literature. And these are the ones that sort of crash out in the literature that are seen to aggregate, are seen to self-assemble. VFF, FFF, LFF, CFF, there's a trend, FFV. VYV, all these things are shown to self-assemble, and we indeed at the AP score of 50 nanoseconds already, they're all above 2. The only borderline case is VYV, which is at 1.88. If we push it further in time, it does indeed become an AP score greater than 2. DFN, ECG, we predict to not self-assemble, and indeed they don't self-assemble. And then we've gone ahead and made the ones which we have selected from our hydrophilicity corrected scale. And I can tell you that we were able to isolate the first tripeptide that's been shown to form a hydrogel using this process. I won't tell you what it is at the moment. I can tell you that the APH score was number 28, so it was down in the list, but we picked it out for reasons that it was that made us think it was interesting, and it was synthesized and characterized, and you see the AFM of it there, and it looks rather nice. We pushed that out to 9.6 microseconds. So you see at 400 nanoseconds, it's all a bit bitty, but once you run the simulation larger and longer, then indeed you get branched fibers forming, which is what you see experimentally. You can, once you have 8,000 dry peptides, you can start to pull design rules out. You can start to find trends, and that's something else that we've been doing, looking at the roles of specific groups. But I'll just finish quickly by saying that what we think we have now is a computational method to pick interesting self-assembling peptides from a database. So you just put all peptides in, you find out which ones self-assemble, and then you put in the different filters that you require. So if you want catalytic peptides, or if you want things that could mimic serine proteases, you pick out only the ones for serine, for example. So that we believe that this can lead to the discovery of new biomaterials and also the design rules once you have all this information before putting in a lot of experimental effort. So I'll stop there and thank the people who did a lot of this work, my students and the collaborators that I've been talking about today. Billy Kerr works with me on the iridium catalyst. Pete Scabara does the organic photovoltaic materials. And Ryan, who you all know, does a lot of the peptide self-assembly work that I've been talking about this afternoon. So thank you for your attention.
Thank you very much, Sal. Any questions? Hiroshi.
So you showed in simulation that basically spherical aggregation or non-shape aggregation turn into the tubular or wire structure. What is the driving force for that?
I think the driving force is always going to be, in these cases, that you're able to get more water molecules free. In other words, hydrophobicity. That if you move into that shape, which is more tubular, then you don't have as much water on the inside that you do on the micelles, and that then frees up more water to interact with more water, and it's just a more thermodynamically favorable state in terms of, I think, both the entropy and also the enthalpy.
So more like, so structure-wise we can more predict, but if you look at the time sequence and short time scale, we see those transitions.
Mm-hmm. Yeah, you see them, how they go. The timescale can't be related directly to the experimental timescale. We work at much higher concentrations in order to force these things to happen quickly.
Right. So let's say we want to design some peptide that you don't want to make tubular structure.
Mm-hmm.
Then all you just need to do is just reduce the hydrophobicity, or is that any better? You know, in combining with the theory, can you really more precisely or more effectively predict the or design up the assembled structure by tweaking the amino acid, for example?
Yes, I think this is a simple answer. Have we done it? No. But that's not something we looked at. We do see that we get tubes, we get fibers, we get micelles, we get amorphous aggregates. We do see a range of different structures. And I think you could very simply go back and just put that filter on and say, okay, let's pull out everything that formed some type of fibrous structure that wasn't a tube. Do we see a trend? Do we see that works when the AP score is between this and this, or the hydrophobicity is between this and this, or that you need to have this amino acid in this position? You know, I mean, you can go back and post-analyze the data. That's what I think is one of the really powerful things about. You end up with this enormous data bank, but then you can go back and put lots of screens on top of it to find out different properties without having to re-go through the effort of running it.
For that ultimate structure, basically it seems like it's largest the minimum for the potential. So
Sorry, say that again.
so let's say again the aggregate turned into more tubular structure seems to be really deep potential well structure wise. So in that sense, how critical to do a dynamic simulation to predict those structures?
In the case of diphenylalanine, everybody knew what it was. I mean, we weren't trying to show what it was for the first time. We were trying to understand that if we take out all the detail, right, so we don't get anti-parallel beta sheets, which is a proposed structure, because we don't have hydrogen bonds, we don't have all the interactions required to make that. But if we take all that out, can we still get something reasonable? And so that was really the point of saying, are these methods reliable for this? And if they are, to the point that we get something that we think is reasonable and we have the driving forces there, can we then use them to in the case of FF, I'm not trying to say that we've told anybody anything new about FF, except there were some clues about the self-assembly mechanism, but what it forms was well known. It forms tubes of this dimension. They were well characterized. So what we were looking for there was to use that as a benchmarking procedure rather than anything else.
Rita?
I'm not clear what do you mean by self-assembly. If you just have two peptides, seems to me it's non-specific aggregation. We call it self-assembly here. Or if there was any structural specificity, is you can predict or calculate.
Yes. So why do I call it self-assembly? Because what we initially are looking for is just aggregation, whether or not these things come together. But we do see a difference in the overall structure, potentially for different things. Some things look like they are fibers, some things look like tubes. And so I think then that's where we talk about whether they are self-assembled structures, whether they have an actual structure.
So when you have a table comparing experimental results, VFF, if I remember one of them, is there's a structure. So what is that experimental structure?
Oh, okay, yeah. So this is just saying, structure in water, that's probably not a great thing. So we're just saying that was the solvent that it was made in, and then it came out of water. It precipitates out.
So how does it distinguish your aggregation or self-assembly from solubility or lack of solubility?
We can't do that. That is something that would be interesting. What we see is that, these scores here are relatively low, but they're at 50 nanoseconds. So what we were looking for here was our AP score able, at this sort of early stage, able to tell us something predictive, what would happen. Whether or not it stays in water or comes out of water, we can't see that from the simulation because it's in a box. It's fixed as is. But that's why we brought in this hydrophilicity index, because empirically we know that if it's really hydrophobic, it's going to crash out of the system. So what we wanted to do was choose things which were more hydrophilic. And so that's why we changed the ranking based on the hydrophilicity. But we don't see that from the data. We don't see something crash out. Yeah.
Gabor?
Do you think that this method can potentially help you also predicting the aggregated or assembled structure? Can you control what you get with the sequence? Like you mentioned, some of them forms tube-like structures and fibers or spherical. Can you use this method to predict that, to control what you get?
Not control what we get, but predict what we could get. Yes, because if we change the sequence, we do see that we get different structures. I think this is going back to what Hiroshi said. We haven't done that before. We haven't said, okay, we want to make sure we only get fibers, and therefore we want to select the things that would give us fibers. I think we could, but we haven't. But I do think it's possible, at least potentially. Yeah, I don't know what would happen once you did the analysis, but you would have to do it to find out.
But sorry.
Yeah, go.
How do you know the fiber you see in this aggregation is not trapped in local minimum? How you start the system?
Yeah, that's a good. Sorry. It's definitely not from how you start the system. We always start with a completely random distribution. So we don't put things as fibers or spheres or anything. We start with this very random distribution and then allow it to form something. You know, but if you look at this example on the screen now, you see at 400 nanoseconds, these look like small sort of amorphous aggregates. And what we see in the end, we have to push this to, I think we actually see fibers at 6.5 microseconds. But that's a long way further down before you get to the fibers. So there is going to be a time dependence. So you may have to refine the data to get to the final structure. I mean, when do we get to the equilibrium structure? This is what we're sort of now finding out. If we push it and push it and push it, at which point does either it breaks or it comes to some equilibrium structure. In some cases where it happens very quick, like FF, there it's going, because it so strongly wants to be together, then that happens really quickly. But in the case of our more hydrophilic things, that's a slower process of things aggregating and then finding eventually the right structure.
I might have missed it, but can you explain a little bit about SWY 0.1?
It's it's just the name of a conformational program. It's a heuristic method for optimizations, and so it uses particle swarm optimization and colony. Yeah.
Is that the program that you made?
It's not a program I made. It's a program a colleague of mine has developed.
It's not available.
It's available. I think you send him an email and he gives it to you for free, and you will try to work out the how to use it. That's a bit tricky, but it works.
Yeah, Hiroshi.
I really like, fascinate this trimer peptide aggregation. So, a little bit going further. So once you make this, in simulation, you're aggregating it. Then, in the effect of the water, can you predict the how this trimer have the angle, so that so potentially, let's say, I'm talking about a triad, for example, right? Mm-hmm. So let's say we have a triad and making the trimer, and they aggregate. And if the surface of the trimer have certain conformation that you can predict, then you can predict that how they can be active or deactivated. Right? So along that line, I'm curious that how can you see that how the tripeptide can be make a conformation upon aggregation?
Yes. So one of the things where we've looked at this, and this was one of the, because trying to get data from these things to compare with is notoriously difficult. People do them, they do them in the solid phase and so on. But one of the data points that we had, and I'm going back to FF, which is the best one that we have, is that you see a rotation of the diphenylalanine side chains. I mean, they start like this in diphenylalanine. When they aggregate, they're like this. And we started all of ours like this. And indeed, what we see was when we got our aggregates, they were all sort of averaged around 0 in this case. So we are seeing effects like that, and we can. It does depend on the amino acid to a degree, because you are going to lose data in terms of the size of these things. Because I'm just skipping back to this image here. Right, I mean, if you have something like glutamine, then you can't see the CON rotation, because it's all just one bead. It's all just captured into one point. So you don't have that. You will have the direction that it's pointing, but finer directionality than that you don't get. So you get the relative orientations of the side chains, but within groups within that side chains, you miss that.
So the FMOC is not on the simulation?
The FMOC. No, these are all just amino acids. So there's no functionalized peptides in this. that is again something that we're working on. We have a parameterization being developed for FMOC, but it becomes trickier with these things.
Okay, are there any further questions? Well, thanks very much for the discussion, and thanks again, Tel, for an excellent
Thank
talk.
you.